Download this code from codegive.com, link in the description below. Handling circular dependencies between Python classes, a deep dive. Circular dependencies, also known as cyclic dependencies, occur when two or more classes are mutually dependent on each other. In simpler terms, class A relies on class B, and class B relies on class A, or on a class that eventually depends on class A. This can lead to import errors, infinite recursion, and generally messy code. Python, being a dynamically typed language, allows you to get away with this in some cases, but it's generally considered a bad practice that leads to hard-to-debug problems and code that's difficult to maintain and reason about. Understanding the problem. Consider this example. Let's put them in separate files for demonstration purposes. Class_a.py asterisk. Class_b.py asterisk. Main.py asterisk. If you try to run main.py, you'll likely encounter an importerror or something similar, because when class_a.py tries to import class B, class_b.py is not yet fully defined. Simultaneously, class_b.py is trying to import class A while class_a.py is still being imported. This is a deadlock at the module loading stage. Even if you somehow circumvent the import error, using delayed imports or other tricks, you might run into infinite recursion issues at runtime if your methods call each other in a loop. In the example above, class A.do_something_with_b calls class B.sum_ method, which calls class A.do_something_with_b again, resulting in an infinite loop and eventually a recursion error. Why are circular dependencies bad? Tight coupling. They create a high degree of coupling between classes. Changes to one class are more likely to require changes to the other, making the code brittle and harder to evolve. Reduced reusability. It becomes difficult to reuse one of the classes independently in other parts of your application or in different projects. Difficult testing. Testing becomes more complex because you need to mock or instantiate both classes to test either one. Increased complexity. Circular dependencies make the code harder to understand and reason about, leading to bugs and maintainability issues. Import errors. As shown earlier, the Python interpreter can have trouble resolving the dependencies during import, leading to importerror exceptions. Runtime errors. Circular method calls can result in infinite recursion and recursion error exceptions. Strategies to resolve circular dependencies. The key is to break the circularity by introducing an intermediary layer or rearranging the responsibilities of the classes. Here are several common strategies. 1. Dependency injection, constructor injection and setter injection. This is a fundamental technique for decoupling classes. Instead of a class directly creating or importing its dependencies, those dependencies are passed in from the outside. This gives you more flexibility to manage dependencies. Constructor injection. Dependencies are provided as arguments to the class's constructor, __init___. This is generally preferred when the dependency is required for the class to function correctly. Setter injection. Dependencies are provided through setter methods specifically designed to set dependencies. This is useful when the dependency is optional or can be changed later. Let's refactor the initial example using constructor injection. Class_a.py asterisk. Class_b.py asterisk. Main.py asterisk. Explanation asterisk. We removed the type hints to avoid importerror caused by circular imports. We created class A and class B instances first with placeholder values, none in this case. After both instances are created, we set the correct dependencies using a.b equals b. This breaks the immediate circular import dependency. Important note: this still has the infinite recursion issue if you uncomment the second assignment in main.py, b equals class b, class A, as that introduces another class A that hasn't had B assigned to it yet. This emphasizes that simply avoiding the importerror doesn't solve the fundamental design problem of the cycle itself. We need more substantial refactoring. 2. Interface or abstract base class, ABC, abstraction. Create an interface or abstract base class that defines the common behavior expected by both classes. Then, have the classes implement that interface instead of directly depending on each other's concrete implementations. This adheres to the dependency inversion principle. Example **. Explanation **. We define an interactor abstract base class with an interact method. Class A depends on an interactor interface, rather than directly on class B. Class B implements the interactor interface. The main.py file now creates a class B instance and passes it to class A, satisfying the dependency without creating a circular import. This makes the design more flexible and reusable. Class A doesn't need to know the specific implementation of class B, it only cares that it can interact with an object that implements the interactor interface. You could easily create other interactor implementations without modifying class A. 3. Move shared functionality to a separate module. If the circular dependency arises because the classes share common logic, extract that logic into a separate module. Both classes can then depend on this new module without creating a cycle. Example **. Let's say class A and class B both need to perform some complex calculation. Calculation_module.py*. Class_A.py*. Class_B.py*. Main.py*. Now, both class A and class B depend on calculation_module, but there's no circular dependency between them. They no longer need to import each other directly. 4. Refactor and merge classes, if appropriate. Sometimes, the best solution is to realize that the two classes are doing very similar things and should actually be part of the same class or a single, more cohesive abstraction. This avoids the dependency problem altogether. This solution strongly depends on the context and the specific responsibilities of the classes involved. 5. Use events/signals, observer pattern. If the interaction between the classes is based on asynchronous notifications, you can use an event system, like the observer pattern, to decouple them. One class publishes events, and the other class subscribes to those events without directly depending on the publisher. Example **. Explanation **. Event system manages event subscriptions and publishing. Class A publishes an event when it does something. Class B subscribes to that event and defines a handle_A_event method to respond when the event is triggered. This approach completely decouples the classes. Class A doesn't need to know anything about Class B, and Class B only knows that a specific event might occur. 6. Lazy imports, use with caution. This is generally not the preferred solution but can be used as a temporary workaround in certain situations. Instead of importing the class at the top of the file, import it only when it's needed inside a function or method. Warning **. Lazy imports can make your code harder to read and understand. They can hide import errors until runtime. They can affect performance if the import happens frequently. Only use this if you have no other options and understand the consequences. 7. Forward declarations, using strings for type hints. You can use strings for type hints to avoid immediate import requirements, which can help with circular dependencies during type checking. However, this only addresses the import issue at the type checking stage, example with main.py. It doesn't fundamentally resolve the underlying design issue or the possibility of runtime errors. Choosing the right strategy. The best strategy depends on the specific context of your classes and the nature of their interaction. Consider these factors. Coupling. How tightly coupled are the classes? If they are highly dependent, you might need to refactor more aggressively. Reusability. Do you need to reuse the classes independently? If so, aim for loose coupling. Complexity. Choose the simplest solution that addresses the problem effectively. Performance. Consider the performance implications of different strategies, especially with lazy imports or event systems. Best practices. Dependency injection. Embrace dependency injection as a core principle of your design. Single responsibility principle. Ensure that each class has a clear and focused responsibility. If a class is doing too much, it might need to be broken down into smaller, more manageable classes. Solid principles. Apply the solid principles of object-oriented design to create flexible and maintainable code. Code reviews. Have your code reviewed by other developers to identify potential circular dependencies and other design issues. Static analysis tools. Use static analysis tools, like Pylint, Flake8, and main.py, to detect circular imports and other code quality problems. Example scenario and solution. Let's say you're building a simple game with player and item classes. The player can hold items, and each item belongs to a player. This creates a potential circular dependency. Initial, problematic, code *. Solution using interface abstraction and dependency injection *. Explanation *. We created an owner interface that represents any class that can own items. This provides an abstraction that both item and player can use without directly knowing the exact type. Item.set_owner makes a call to owner.add_owned_item, self, but the owner interface declares this method, rather than directly calling players @_item method. Item now only depends on owner interface, not specifically on the player class. This breaks the circular dependency. This approach offers flexibility. You can now easily introduce other classes that implement owner interface, example a chest class, without modifying the item class. In conclusion, circular dependencies are a common problem in object-oriented design, but they can be effectively addressed using various techniques. The key is to understand the underlying problem and choose the strategy that best fits the context of your classes and their relationships. By embracing dependency injection, interface abstraction, and the solid principles, you can create more flexible, maintainable, and testable code. Remember to prioritize clear communication, well-defined responsibilities, and loose coupling in your designs.